Hello and good evening everyone. My name is Shraddha Mukherjee and in this video we will be studying a particular portion in atomic structure which deals with wave-particle duality of an atom. So what do I just tell you? We will deal with wave-particle duality. Now, how do we reach to this wave-particle duality? The first thing is, when the subatomic particles, especially the electrons and the protons and the neutrons are discovered, scientists from all over the world are very keen to know their arrangement inside the atom, how these subatomic particles are arranged inside the atom, and by this arrangement they try to prove various properties shown by the atom. These were first given by a basic model is given by Sir J.J. Thomson. Then we have Rutherford's model. And then we have Bohr's model. Sir J.J. Thomson's model was a very basic model which we also call palm pudding model, followed by Rutherford models. Rutherford model gives us the idea about the presence of a nucleus where the mass of the atom mainly resides. The nucleus consists of protons and neutrons. But Rutherford model has its own drawback, followed by then the Bohr's model. Bohr tried to explain various spectra, and we have various different types of spectra that can be explained by Bohr model, but the problem is Bohr models was only applicable to hydrogen and hydrogen-like species. But during the quest of this model, it is seen that an atom has some properties which can be explained while considering the wave nature of a particle. Now these scientists what they did is they considered atom as a particle. They considered atom as a particle. And given their theory, but during the process it seemed that there are some properties of an atom that can be explained by considering the wave nature of an atom. Now what is the wave nature and how does this wave nature come into existence? We need to know little bit about its history too. Okay, so it all started, this wave nature thing started in the year, predominantly in the year 1900, when a scientist Planck has stated that the energy emitted is not continuous but it is emitted in the form of small packets and he called these small packets as quanta. Again I am going to repeat. Planck stated that the energy is something that is not continuous. Instead, these are emitted as packets of energy. And these are called quantas. Okay, so quantas. Now what is the difference? What is the difference between these quantas and packets of energy and continuous energy? Let's say we say that in Holi, have you seen, we all have played Holi, or we have all seen everyone playing Holi. So in Holi you can give color by two ways. It means what? One, we can use that our very own, we call it pichkari. okay, in which you just push the water and the water flows away from the nozzle of that instrument. So if you remember, it looks something like this. And the water comes out from this, right? And then another way we can play or throw color in Holi is if we throw balloons. Now let's say that I want to throw someone 3 liters of water. Hypothetical situation, I want to throw someone with 3 liters of water. So this instrument contains 3 liters, let's say, assume hypothetical situation, 3 liters, so I can just throw 3 liters of water from this instrument. And let's say all the balloons have the capacity of 1 liter each. So either I can throw 3 liters of water from this instrument, or I can just throw 3 balloons. So these are both are same options. Both will throw 3 liters of water to the person which I want to throw. Now let's say this. Instead of 3 liters, I want to send 3.5 liters. Now this pitchkari has a capacity, let's say, of 5 liters. So by this continuous process, I can easily throw 3.5 liters. But all my balloons are 1 liters capacity. Can I send 3.5 liters? I cannot send. Either I can send 4 liters by throwing 4 balloons, or I can throw 3 liters by using 3 balloons. So now what happens is I cannot use water that is in between. Now the water, if I am using the balloons, these are quantized. These contain particular quantities of water and whose multiplication can only be thrown. For example, this 1 liter balloon, if I want to throw 3.5 liters, I have to throw 4 balloons, 4. That consists of 4 liters. Similarly, when the energy is continuous, I can send immediate amount of energy, any amount of energy. But when the energy is in the form of packets or quantas, I cannot send them in random way. Instead, they will be the multiples. They will be the simple whole number multiple of individual packets. Right? So now we got this, what are quantas and Planck gave an expression for energy also. He gave the expression for energy E equals to h nu, where E is energy, nu is the frequency, and h we call it Planck's constant, which have a value of 6.6 into 10 to the power minus 34, and the unit is joule second. All of the unit of Planck constant is joule second. So Planck first started about talking the energy which is continuous, which is in the form of quantas. Okay. Now cut to after 5 years, 1905. In the year 1905, Einstein gave his hypothesis that the light also consists of energy in the form of small packets, and he named them photons. He names them, the energy of light, as photons. So whatever Planck has told them, Einstein has used this property for light, and he stated that the light also contains particles or packets of energy, and he calls them photon. By this principle, Einstein can explain, or we can explain, a photoelectric effect. Now, what is a photoelectric effect? let's say this is a metal surface. This is my metal surface, and whenever light of a particular frequency falls on it, an electron will be emitted from the surface of the metal. Whenever light of a particular frequency falls on it, the electron is emitted from the surface of the metal. Now, will any light falling on the surface of the metal will emit an electron? Absolutely not. Light of certain particular frequency will emit electron, and frequency higher than that won't emit. Now let us say if I consider classical physics, now understand this with the help of this example. Let's say I have two beakers. Let's say I have two beakers, and both of them I have put it on a flame. One flame is high flame, another flame is a lower flame. Both contain, let's say, same amount of water, that is 1 liter. Both contain 1 liters of water. Now tell me, which one will boil faster? Which one will boil faster? Obviously the one which has a higher flame will boil faster and bubbles will start coming out of it. How much time it will take? Let's say I assume it. Let's say it will take 5 minutes. Now will the water with a lower flame won't boil? You will say, no, of course it will boil. But instead of 5 minutes, it can take what? It can take some longer amount of time. Let's say it takes 10 minutes. So over here what is happening is energy is continuous. Over here the energy is continuous. Let's say 5 minutes, because the energy is higher, 5 minutes. For 10 minutes, when the energy is lower, heat energy is lower, then it will take 10 minutes, but eventually the water will start boiling. So if the energy of the light was continuous as based on classical physics, so if I incidented a light of lower energy and if I incidented it long enough, so after some time an electron should emit from the surface of the metal, right? Let's say green light is emitting energy whereas red light does not. So if I point the red light for certain amount of time, let's say green light is emitting energy instantly in 1 second. This green light is emitting an electron instantly in 1 second. If the energy was continuous and I put a red light of lower energy, then maybe after 10 seconds an electron should have emitted. But what happens is, we saw that the light of particular frequency does not emit an electron until a certain value of energy is reached. Below that energy, the frequency of that light won't emit any electron. This can only be proved by if we consider that the energy is quantized. Let's say someone has a lower energy and the quanta shape is small, just for the sake of understanding. These are small quantas, okay? And someone with a higher energy has higher quantas. Now this is my limit. Below this, it won't emit. Below this, whatever the frequency, how much will be the time, it won't emit. After this, they will start emitting the electron. And the frequency which leads to this energy, we call it threshold frequency. Right? So now we have understood some things. Let us just quickly jot down the points that we have discussed. Firstly, the atomic structure started when the scientists considered atom as a particle, but certain properties of atom can be explained by considering the wave nature. And how does this come into play? First, it was started by Planck who gave the Planck's constant and the formula E equals to h nu. Then this, and he called that the packet of energy as quantas. Then it is followed by Einstein in 1905, who gave the hypothesis that even light shows dual nature, and he could explain the property or the phenomena of photoelectric effect by considering the light, considering that photons. Okay, when the photon of certain frequency pass the threshold frequency, it will emit the electron. Below that, it won't emit. Now, how does it comes to atom? The next question lies in how does this come to an atom? In this context, it comes to our atomic structure, and with this, we will discuss two scientists, that is de Broglie's equation and Schrodinger's uncertainties principle. The first scientist is a French scientist, if I am not wrong. His name is Louis de Broglie. Louis de Broglie stated that all the microcyclic, all the micro and macro particles will have both particle nature as well as wave nature. Okay, let me repeat it. De Broglie stated that all the micro as well as macro particle will have particle nature as well as wave nature. What are the microparticles? Microparticles are my electrons, protons, neutrons, atoms. These are my microparticles. What are the macroparticles? The chalk that I am holding is the macroparticle. The ball or anything that you see around you is a macroparticle. So de Broglie stated that all the particles will show both wave nature as well as particle nature. So de Broglie, what he does that he used the energy formula given by Einstein, given by Planck's, E equals to h nu, and he taken the Einstein's particle formula equals to mc square. When we consider this equation 1 and equation 2, he just equated the two equations. So I can write down h nu equals to mc square. Nu is my frequency, so nu equals to c by lambda. This is the formula for wave. So by substituting the value, I got hc by lambda equals to mc square, got the c. So lambda becomes h by mc. Now c is the speed of light. Now everything is not moving at the speed of light. Instead of considering c, we can consider this as v, which is the velocity. So I can write this as lambda equals to h by mv. This is an expression for de Broglie. mv, mass into velocity. Mass into velocity is p, which is momentum. So lambda can also be written by h by p. This is another expression for de Broglie's. So de Broglie's have two expressions, lambda equals to h by mv and lambda equals to h by p. Okay. So de Broglie stated that all the macro as well as microparticle will consist of both wave nature as well as particle nature, right? And what is the wave nature? And he considered the two formula, one by Planck's, one by Einstein. He just equated it and just solved the formulas, and he got the two expression. We got the two expression, and these are my formulas, right? Okay. So now there are some drawbacks also for de Broglie. What is the drawback? I think you have copied this one. One of the drawback of de Broglie is it says that wave nature and particle nature exist for both macro and micro particle, but the wave nature of this macro particles, these are, for example, this chalk, this ball, or something like this, became so negligible. Excuse me. Became so negligible, but so that we cannot calculate it, or we can calculate it theoretically, but such intricate instrument we does not have that can calculate this wave nature of this, let's say, chalk, or let's say a cricket ball, or something like that. With this, we will next move on to our next scientist, that is Heisenberg, who had proposed Heisenberg's uncertainty principle. The de Broglie's this hypothesis and the limitation, we will try to solve it with the help of an example also. First we will discuss Heisenberg's uncertainty principle, and then we will do a numerical to explain what is the limitation for de Broglie for macro particles, right? Heisenberg's uncertainty principle. Heisenberg's uncertainty principle stated that for a microparticle, the position and the momentum cannot be determined with complete accuracy simultaneously. Cannot be measured accurately simultaneously. Now, again, let us understand this by the concept of a macroparticle and a microparticle. Let's say a macroparticle, I have a ball. Let's say a cricket ball, and the ball is moving in this direction. So is it possible for me to know the position of the ball as well as the momentum of the ball? Of course it is possible. Let's say when we play cricket, okay, the ball is hit. We can, at the certain point, we can understand that this is the position of the ball and this is the momentum of the ball. The velocity with which it is moving in that trajectory, we can accurately determine the position as well as momentum for a macrocyclic particle. But when it's come to microcyclic particle, Heisenberg said that we cannot determine the position and the momentum of a particle simultaneously and accurately. Okay? Why? Now the question comes, why? Now understand this. Let's say this is an electron. And electron is hypothetically moving in this trajectory. Now I need to find the position of this electron. So I will see through a microscope that where the electron is. This is my microscope. And via this microscope I can see the position of this electron, right? But to see the position of this electron, I need a source of light. So whenever a light falls on this, light contains energy. Whenever the light falls on this electron, the light contains energy in the form of photon. So electron will instantaneously absorb the energy and will change its trajectory. What is happening? The electron was evolving something in its own path. I want to see the position of these electrons accurately. So I use the source of energy. As a source of energy, light, and I am watching it through the microscope. So whenever the light falls on it, the electron will acquire some energy through the photons and will instantaneously change its trajectory. So I cannot find the exact position of the electron. Same goes for momentum. The velocity will change, and its momentum will change. So the Heisenberg has given an expression to justify it, and the Heisenberg expression goes like this: del x, that is the del means change of something, change of position, del x into del p, that is change in momentum, is more than or equal to h by 4 pi, right? Now remember this, sometime in quantum mechanics we h by 2 pi we use that as h cut. Okay, this is something, if you are doing some numericals, we use h by 2 pi, we simply write this h cut, but we will consider over here h by 4 pi only. Okay? So del x, that is change in position, and the change in momentum is more than or equal to h by 4 pi. Now momentum, if you remember in de Broglie we use the formula mv, p equals to mv, mass into velocity. So del p will be mass, that is constant, mass won't change but velocity will change, m into del v. So we can substitute the del p value in this equation. So del x into m del v is equal to h by 4 pi. Bring the m in this side, what we will get? If we put the m in this side, we will del x into del v gives h by 4 pi m. This is my another expression for Heisenberg's uncertainty principle. So the Heisenberg's uncertainty principle also has two expressions, deduced it. One is del x into del p into h by 4 pi is equal more than or equal to h by 4 pi, and del x into del p equals to h by 4 pi m. So these are the two scientists that talks about the wave and particle nature of an atom. Now the next question is, what is the use of it? So when we consider the wave and particle nature of an atom, then it was used by another scientist called the Erwin Schrödinger. He gave an expression which is used for next 100 of years, and we use it till now to understand the position of an electron, and we move from the concept of orbit. If you have studied both model, both talks about orbit, stationary orbit, non-stationary orbit, what is the stationary orbit, what are the criteria for stationary orbit, so on and so forth. But now, since we know that we cannot determine the exact position of an electron, so how can we consider electron as a localized particle? So from this orbit, we eventually move to the concept of orbitals. Orbitals does not talk about the exact positions, instead it talks about its probability of finding the electron. I cannot say that I will find the electron over here, but I can say that, okay, I know that the electron exists somewhere over here. So it moves from orbits to orbitals, from exact position to probability of finding something. So on and so forth. This starts with the contribution of two scientists, the de Broglie's equation and Heisenberg's uncertainty principle. I hope you have understood this concept. These are a bit tricky as it is an inception to quantum mechanical, but these are very interesting topics, and I hope you have a great time learning. Thank you for your time. Thank you everyone.